Thank you, Mira. So my presentation will be slightly different than from previous speakers. You will see a lot of colorful pictures, which I hope you will understand, or I will try to make you understand. And I have some good news and I have some bad news, so be prepared for it. And it's addressing two topics that Professor Habersack said he will skip. It's about climate change, about land use change that is involved in this. And this is about the water, energy, food, and we like to add the word environment as well, nexus. So these things are related. We at the JRC of the European Commission, we started to intensify our work a few years ago. We decided to take the Danube as a pilot basin. But before we went to the full Danube, where we are now, we did also a pilot study in the Sava. So some of the results you will see are specifically for the Sava River Basin valid. The idea of the nexus is that all these things are interrelated. Obviously, with water quantity, we have the two extremes, and they are problems and they're costly, and you want to solve them. But if you solve them, you affect the other sectors. If you take flood protection measures, you might affect navigation. If water is used for cooling, it isn't available for irrigation. If water is used for industry, it isn't available for the environment. And there is an important concept here. Also, the environment needs a minimum amount of water to be healthy for the ecology. What that minimum amount is still a scientific issue, but it needs a minimum amount. Agriculture needs a minimum amount, depending on how much irrigation there is or how much rain-fed agriculture there is in an area. And obviously, navigation has its minimum standards already mentioned by Professor Habersack. Industry needs water for processing, for cooling. Tourists like to be at a nice lake or at a riverside or with the boats on a river. And of course, we have the human water consumption. And then there is societal change, there is climate change. However certain or uncertain the quantities are, and that will result into changing demands. So we have changing availability and we have changing demands. And how will they fit, and how can we find an optimum? That's a bit of the idea of the nexus study we are doing. So we want to match water demand and supply. And the aim is to have sufficient water for all sectors. So not only, reduce flood risk, but at the same time, try to meet the requirements of agriculture, of the energy producers as well, and of the environment, to have sufficient minimum flow. So to have also sufficient energy production in the country and a sufficient food production in the country. And obviously, if you want to do that, that will have costs. So we try to take the economic side also on board. The cost of the implementation of measures and the maintenance of measures, and let's say the results. What are the costs or the benefits you get back? Is there increased or decreased flood damage? And are there other direct or indirect benefits of certain measures? So we work together with a team of economists as well in this study. We decided to do the Danube as a pilot, although we work on European and also actually on global scale since a few years. Supporting the Danube strategy, we have the water, food and energy nexus. We also have a group at JRC addressing air pollution and the air problems, the land and the soil nexus. So these contains a lot of soil specialists, and we have a bioenergy group working also in the Danube. It's important to realize that whatever we do, and some of it is already available, we make the results available to everybody. So all the results and data we have are or will be available on the portal that is already open, and you can find lots of products. We also link to existing products from other projects, but also our own data will go on there. So what do we try to do? We want to provide an overview of the current water resources and pressures in a river basin. And then also look at the future. If there is changing climate, changing society, changing measures, we will have changes in water demand and water availability. And we, for a number of reasons, we focus mainly until 2050, because then we can more or less still project societal change in Europe. Beyond 2050 it becomes really tricky. Obviously sometimes for a climate change horizon we go to 2100 or a little bit beyond that. But for more down-to-earth things we stick to 250. That's already difficult enough. So we try to include additional climate change effect, and then we try to, on top of that, evaluate policy measures, because that's our role in the Commission, and that's also the role of the member states to take measures, and our role is more or less to see what the effect is of those measures that member states take, and sometimes we suggest alternative measures or additional measures. We look at water as a whole, so also at the extremes, but also at the availability for hydropower and for thermal power. We work together with energy groups in the JRC and beyond the JRC to look at the power production possible, and if you take measures, how the power system changes and if that still meets the needs of the national power system. And we work with our agricultural colleagues in the JRC and an external network to see what the effects are on food production and what are the options for increased irrigation or for optimized irrigation to reach the required crop yields. So we took the Danube and the Sava as a working area for a moment. So we finished the pilot in the Sava River Basin last year, basically, where we did some initial runs. We interacted pretty heavily and I think quite positively with the Sava River Commission, because that's, the aim of what we do is we can never be as precise as local groups, and that's also not our aim, but we want to be precise enough or sufficiently precise that it's still relevant at local level, although we work at big river basin level or at continental level or at political level. We still try to be locally relevant. Since the Sava pilot, where we learned a lot, we did another thing. In JRC, we make a land use projection, so we make land use predictions, just like you make climate predictions. We predict the land use up to 2050 based on agricultural policies, energy policies, national plans, regional plans in Brussels. But so far we did that for EU 28. So Croatia was involved, Slovenia was involved, Hungary was involved, but Serbia was not. So we realized that, and in order to do a full Danube analysis, we did an initiative to add Serbia, Bosnia and Montenegro to that land use projection, and that's now finished. So we had a workshop last year, and we included some experts to get some additional information from the countries, how difficult it is. This is just state of the art what we can do, and obviously in 2 or 3 years we probably have to do an update, because predicting the future basically changes constantly. But we now just finished a land use projection, including a projection for Serbia until 2050. I don't have all the results with me yet. I will show you a little bit what we have done so far, but we finalized the complete analysis before the end of the year. And we're now running all that in the Danube. So we make an hydrological prediction or simulations for the Danube, including climate change, land use change, and on top of that, additional measures, for instance, irrigation. And I will show you a few results. We do this through a hydrological model that we developed at JRC since quite a long time. This is the same model that is the operational part of the flood alert system that is active all over Europe, and also the model that is used in the drought alert system that we have at JRC. Over the years we have expanded that, and also recently we have a major overhaul of the model. So it did already include reservoirs and lakes, but now we have embedded irrigation in the model. So the model automatically calculates the amount of irrigation needed to grow a certain crop, depending on changing weather or changing conditions. It does water abstraction, either from groundwater, from surface water, or from lakes or from reservoirs, whatever you give in, but you can make a distinction. So there is also a mimicking of the groundwater storage. It's not a full-blown groundwater model, but it has at least a simulation of the amount of groundwater, and you see if you start depleting it or if you keep the groundwater amount sustainable in the long run. And then there's routing and everything. It's a grid-based model, and for the Danube we use a 5 by 5 kilometer resolution. We actually run this globally as well now, on a 0.1 degree. Obviously, we calibrate that. We used, 700, close to 1,000 stations in Europe that were good enough for calibration, because there's many more, but you can't use them all because they have too short or uncertain records. We happily worked also with the Sava Commission, the yearbooks that were produced here, some data by the Global Runoff Data Center. It's a hierarchical calibration, so you have sometimes upstream areas that you first calibrate and then you move on further downstream. So I must say, I think on the European continental level, this is probably the most precise model that exists at the moment. Obviously, at local scales, you have better ones, but at a continental scale, I think we do quite well. We come to land use change. Like I said, we have a land use prediction model that goes to 250, and we just finished simulations including Serbia, Montenegro, and Bosnia. I didn't analyze the full results yet. That will come later this year. From previous work, and that's on the left side, there is a few interesting things to take into account. Somebody was also mentioning that it's difficult to predict the future of water demand. One thing that you see in the curves on the left side, I hope you can see the colors, this is projected population change in Europe. Europe as a whole, if my mouse is working, yeah, I think this is the EU level. So it's basically slightly increasing. This is the 0 level here. So Europe is staying more or less constant, but I think these are, I can't see it precisely from here because this is Hungary and I think Croatia, and they have at least a prediction for population decrease, 10 to 15%. It is a projection done by experts. I'm not an expert in this field, but this is something to take into account, and this will have a consequence that probably the water demand from the public sector might go down. What you also see, you see an aging society. I have a PhD working on this, so we know a bit more details on this. A lot of societies are aging, and elderly people tend to use less water than younger people. So together with the population decrease and an elderly aging society, you get a decrease in water demand. On the other side, there is still an unclear effect, and that's about household composition. If you have smaller households, a 1 or 2 person household, effectively they use more water than a 3 or 4 person household. So you have also an effect that might balance it again. If you have smaller households that they tend to use a little bit more. So predicting household water use is not an easy thing. And then there's also price involved. Obviously, if you increase the price, people tend to use less water. That's actually what we do also. So this is, for example, this is the full Danube now. So you see a picture here. This is the projected change in urban areas, so basically urban growth from the baseline, which is 2006, 2010 to 2050. So basically, almost, well, there are areas with a slight reduction. That's typically the countryside. And you see almost everywhere the agglomerations of the big cities. So you see Belgrade, Budapest, Munich, where you see over the years an increase in sealed area in the already urban area. So that's a tendency that you basically see, or we project almost everywhere. And obviously this has a consequence later also for potential flood risk, because in this case all these major cities are along the Danube. So I will come back to that later, because all these things are interrelated. Talking about land use change, so what we then do in the nexus, because it's all about water demand of various sectors, and one of them is the household water consumption. We try to understand how the household water consumption functions in every country, and every country is different. Every country has a different water price. Some countries have a completely different climate. Obviously in Spain it's different than in Denmark or in Norway. There is a GDP difference, so in Norway the price of water might not be a factor for people. They just use whatever they need, where in another country if the price is high it might be a factor. So all these economic relations are different, and we use that to predict future water consumption, and also we use that to predict changing consumption if you change the price. We try to do the same for industry. So we get from the land use people and from the economic people, we get projections if industry is growing or industry is not growing. Then we try to estimate how much water the industry needs to produce its goods. And we also try to estimate the damage, the potential damage, if the industry doesn't have the water it needs. Let's say you're in a water scarce situation, and then it depends really from one industry to the other and from one country to the other what the potential damage is that the industry might have. And that plays a role if you try to optimize the water nexus, because it might be, in the end it's a political decision, but if you want to do it based on economics, you might have a preference to leave the industry, to give the industry its water, because that is economically more important. And sometimes say to a farmer, sorry, forget about your maize crop this year. We have to make a choice, and in the end, that is more cost effective. How you treat that politically is a different thing, but economically you can think that way. So the same way we do it for agriculture, we try to estimate what happens if there is a water scarcity, and what is then the damage for a farmer, or what is the consequence for a farmer income. We don't do this alone. We work with agricultural economists to do this. Then we try to make the whole picture in the hydrological model. From all the sectors, we collected the demand. So this is the picture of the average water demand in the Danube area without irrigation, because irrigation is done in this case automatically. Then the model, basically what the model does, because this is demand, the model then wants to abstract it from the natural system, but there might be cases that it's not there. For instance, we build into a model an environmental condition, so if there is too little flow in the river, it might not be able to abstract, and then we have a water scarcity situation. Or it abstracts it from the groundwater or from a reservoir, but if the water is not there, it can't do it. So demand is not automatically abstraction. In many cases it is, but then you have abstraction, but abstraction is not consumption, because drinking water you consume, but in the end it flows back in some way or another as wastewater to the system. So the actual consumption, so typically the water that evaporates or that is part of a crop or part of an industrial product, is this picture, so these values are much lower. So this is the actual water that you lose from the system. And then we try to integrate this and go into the future if all these things matches, if they match. So we have been using up to now 5 climate scenarios, and this looks at the effect of a 2-degree change in Europe. So this takes basically as if the Paris Agreement that was reached in December, if that is executed in Europe. And that's the good news. That's in the next picture. This is an average of 5 climate models over Europe with the effect of a global 2-degree scenario. 2-degree is globally. That doesn't mean that it's everywhere in Europe. For example, the Arctic region in northern Norway, northern Russia, would have temperature increases far higher than 2 degrees, that can go to 5 degrees almost, with the global 2-degree scenario, where on average for the Danube and for Central Europe, it's between 1 and 1.5 degrees. So that's the temperature effect that goes with the Paris Agreement if it's completely executed. On the right side is the precipitation change as a consequence of this 2-degree climate change. And if you look at the numbers, the general pattern is the pattern that we've seen before in the last 10 years, the general predictions that it's wetter typically in the north and a bit drier in the south. But if you look at the numbers, it's far less extreme than previous analysis. So that's the good news. It is not as bad anymore, thanks to the Paris Agreement, if it's executed, than previous predictions. There is still an increase in precipitation. This is annual average precipitation. And there is still a decrease in the Mediterranean, but that decrease is only 5%. And previous analyses were up to 30–40% less. So that's part of the good news I wanted to give you. So if you zoom into the Danube, you see on the southern fringe of the Danube, including the southern parts of Serbia, there the projected changes are the highest, so then it's in the order of 1.5 degree, whereas in the northern part of the Danube it's much more closer to 1 degree. So the effects are different. In the Alps it's pretty it's somewhat higher again in the mountain ranges. And for precipitation, you see basically also a north-south trend. So basically in the northern part of the Danube, in general an increase up to 20%, and in the southern part even a slight decrease. But like I said, not as bad anymore as in previous analysis. That's the first observation I make. The model can make many outputs. I will not go into that. It can produce discharge. It can produce soil moisture maps, groundwater amounts, all kinds of indicators. I will show you a few things. So I just have to stress the land use effect is not in here yet. This is only the effect of future climate change on the Danube. And also the irrigation we've started yet, all the measures are not yet included. This is only the effect of climate on the current water resources in the Danube. One thing that we simulate is what I've called the evapotranspiration deficit. So that's a deficit, the difference between potential and actual transpiration goes up, especially in the southern fringe. What does it mean is that vegetation or a crop doesn't have the water it wants to grow, to transpirate. And that means you have less productivity. And this means that if you have irrigation in that area, you probably have an increased need for irrigation to reach the same result. That's basically what you see here. So in irrigated areas already, you probably need more water to reach the same result. A very colorful picture, this one. Medium discharge. This is, let's say, the overland flow pattern, where you're probably more interested because it's pretty colorful. You see both reductions there, the reddish and the yellowish colors, and bluish areas which are increases. You're probably more interested in the rivers. So this is actually the same picture on the right side, but then the river Danube and the bigger rivers extracted. And you see overall there is pretty much still an increase of the available water. And only a very few tiny rivers, they show a decrease of median discharge. And recalling previous analysis we did, this is different than previous analysis. This is much more mild and less dramatic than previous analysis. This has consequences. I've not finished the result yet. We're working on that. We look at the hydropower stations. We don't include them all, like Professor Habersack was saying, because only Austria has already 5,000. We look at the major ones. They are included in a model, and we try to estimate the energy production that comes from there. And we give to the energy people, let's say, the amount of water that is available, and we try to work out with them what then the energy that is produced on the stations. But I won't go into that, but to get energy also in the picture. If we look at the climate effect on the extreme high flows, so more the flood risk, it's this picture. So this is the 99.95 percentile, which is basically somewhere in close to a 5-year flood. I will do the proper return periods later, but this you can compare more or less with a 5-year flood. Again, it's a colorful picture with some increases and decreases, but if you isolate the rivers again, which I do here, this is the bad news, that although the climate change is much more mild with the Paris Agreement, for the Danube, still this flood peak discharge goes up more than 10%, and that's a lot. So flood risk is and will be a very important issue in the Danube basin, and obviously measures are needed for that. But I don't need to explain that to the Serbian people, not the Danube people, because you have been hit by many floods in the last couple of years. And this is also what I said, where urban growth is important, and hopefully there is a good dialogue with spatial planning, because if these urban areas are expected to grow, then for God's sake have a dialogue and don't let them build in a floodplain, because we have these increasing flood problems as well. So this is actually what we also try to do with the land use modelers, that we give them conditions, don't expand in the floodplain areas, but obviously in reality you need to do that with the land use planning authorities, that please plan your urban areas with some intelligence, please. On the low flow side, we get also a picture. This is only the 10 percentile low flow, so there are more low flow parameters, and the river pattern is a bit surprising to me in any case, because that's also increasing. So the low flow problem, at least from this analysis, seemed to go down, which is positive. It's a bit contradictory to what has been said about the Tisa, because there they expect a decrease in low flow. So I will look again at these figures if they're correct and if the other indicators show the same thing, but at least this one shows that even the Tisa, the low flow problem, might go down. Don't believe me, this is only one analysis. There are more models, and I will double check them, but it's in any case something I picked up here that I have to be double checking the Tisa conclusions. We look then also, whatever scenario we do, on the number of E-flow, what I call E-flow breaching days. So you want, basically you don't want that the flow is lower than an ecological flow, but there might always be a few days a year where it happens, but you want to minimize them. So we always keep in mind how many low flow breaches you have, and obviously with the scenario you want to minimize them. Another important indicator is more an overall indicator of a catchment. This is water consumption versus availability for a specific subregion. So these are basically sub-basins. And the thing is, the Danube as a whole, this is not a very water-stressed area with current water consumption. Current water consumption in Danube is relatively low compared to some other international river basins. It might go up in the future, and then you might have increased problems. At the moment, it's not very water stressed. Typically, we call a water stressed area when the water exploitation index is 0.3 or 0.4, and that's only happening in a few sub areas in the Danube. And obviously, climate change will change this a little, but only very little if you look at the numbers. But it will change this in many cases in a positive sense. So because the projections are that in a number of areas it will be slightly wetter than it is now. So the water exploitation index from this analysis is expected to go slightly better than before. But if you change demand and if you heavily increase irrigation, obviously then the picture looks different. This is what we analyzed for the Sava. We will do this now also for the Danube. We have included some extreme irrigation scenarios. I think the director of Jaroslav Czerny already said in Serbia only 40% of the irrigation structures are actually operational. Suppose you would bring that back to 100%. You probably could produce a lot of food. It will be economically costly to do that. The question is the water there to do it? And that's what we find out. And this analysis shows that if you go to the very extreme of irrigation, the water isn't there. And then you get a water exploitation index that goes sky high and goes to a critical point, goes to 0.4 or goes to higher. We also look to, this is more an indicator that is used on a global scale, the Falkenmark index. So how much water does a citizen have on average, and how does it change in future? There are two ways to look at this. This is locally produced water. If you look locally only, there are areas that are quite critical, including the north of Serbia and even Vienna. But obviously, we heard before, Vienna takes its water from upstream. So if you include upstream water, the picture looks much less dramatic, because some regions take it from upstream from the mountains, or some other areas might take it from the big river systems. But this is an indication for how much water is available per capita, and obviously that's what you want to monitor if you have increasing population or things like that. We look at groundwater a little bit, how that is changing, and if it's still sustainable if you start implementing measures. But talking about these measures, and we haven't executed them for the Danube, but we have done it for the Sava, and I will show you some results. There is an interesting thing in this is the Sava basin, and on the left side is basically the current situation. That's the agricultural production of maize, and this is the yield you can get with maize. And on the right side is the potential yield that you could get. And you can increase, if you irrigate it to the optimum level, you can increase the yield from 5.7 tons per hectare on average in the Sava basin to 9.9 tons per hectare, so close to double. So that's a substantial change. But if you do that, it has a cost. Well, this is the actual then production level. So especially in the Serbian area, there's a big potential to do that. But it has a cost, and that is the amount of water that you need. On the left side is what is currently needed for irrigation, with the current maize production and the current irrigation structures. If you would irrigate all the maize in the Sava basin to get to this optimum production, you get the picture on the right side. And what we have done is analyzing if that water is there. And the conclusion was no, it's not there. This is too extreme. It might be very profitable for the farmers, or at least you get a higher yield, but the water is just not there. So this is the irrigated area for the Danube as it is now, and which we will simulate the effects for. This is what, if you use the structures that are there, like in Serbia 40% is there, but you can go to 100%, so this is basically the 100%. And this extreme picture is if you irrigate everywhere where there is a potential need, but this is very unlikely, but just a theoretical maximum of irrigating everywhere where it's needed. And we just want to see what is feasible and what is the limit for agriculture. And obviously then we will also look at the other sectors, because the problem is other sectors will be affected. What in the end, if you combine all this, the model burps out is water shortage. Like I said, the model only abstracts if the water is there. So this is the indicator that in some regions, in some times of the year, the water is not there if you want to respect environmental flow. And then it gives out an amount of water. And this is the projection, how that changes under climate change, and you get actually a slight improvement. But this is the type of work we do for various scenarios. And this is just a picture, the water shortage under this extreme irrigation scenario. For some countries you might be able to do it, but they're probably not interested, like Montenegro or other countries. But in Serbia or in Lower Croatia, you get a huge problem. The water is just not there to do that. So that's the type of work. Like I said, we finished the work for the Sava, but we are still working on the full Danube analysis. I will just make some preliminary conclusions. What we see from the climate analysis is that the Paris Agreement seems to reduce, well, that's what is expected, because if you try to reduce emissions, you hope that there is an effect as well. And from our work, it seems that there is. These things, projections are substantially less dramatic than they used to be. But still you see flood discharges increasing, and it coincides with increasing urban areas. So that needs attention still. Intensifying agriculture or irrigated agriculture, there is a possibility for that. In any case, from a crop yield point of view, there is a potential. Some of the water might be there, but that's exactly the issue that we want to investigate. If you go to the extreme, it's not there. So we want to see what is the critical limit. We're also analyzing with our agricultural colleagues suboptimal irrigation. So you might not want to give 100%, but just give 80%, and you still might get 95% crop yield. So what is there an effective middle way? And all sorts of water efficiency measures. And we're also analyzing that other sectors might be influenced, like hydropower or the energy production sector. They might not have the water anymore that they need, and sectors like navigation. And the full Danube assessment will be finished more or less end of the year. So thank you.